Remember from section 1.6 we talked about what a function is, when a relation is a function. And that was when every input, or every element of the domain, only has one output. Or every element of the domain is only related to one element in the range. Well, now we're going to talk a little bit about function notation, and we're going to discuss how we can write functions using function notation, and also how to evaluate functions for a given value using either a graph of the function or the function rule, which we'll talk about in a minute. And when we say evaluate, we basically mean given an x value, figure out what the y value would be, figure out what the output value would be. So in order to talk about function notation, we have to know what we're looking at. Function notation, you've probably seen it before, looks like this. And we read this as f of x equals 5x plus 3. And this gives us the name of the function, f of x, and it gives us the rule for the function rule, 5x plus 3. So here's the name, right here, and here is the rule, right there. The rule tells us what we're doing when we plug a value in, and the name tells us what we're talking about. Now you might be saying to yourself, you know, this looks really similar to something that I used to write when we would just say y equals 5x plus 3. So why are we starting to write f of x instead of y? Because it's really the same thing. F of x represents the output value, or the y value that I get. Well, it gets a little confusing if we are dealing with a complex problem and we have multiple rules to evaluate. If I said y equals f of x, or correction, y equals 5x plus 3, and then I said y equals 2x minus 6, well, when I told you to plug in x to something, if I said evaluate it for x equals 0, you wouldn't know which one I'm talking about. So instead of writing y, we can write f of x. We can give this rule a name. Now I've written it in function notation. The function name here is f of x. Its rule is 5x plus 3. With this one, if I had to have two different rules in the same context, then I could name it g of x. And the g of x rule is 2x minus 6. So when I wanted you to plug in a value, when I wanted you to use an input, I could tell you evaluate this when x equals 0. But an easier way, now that I have function notation, is take f of, instead of f of x now, I want to take f of 0. So we look at the name f, and that tells me I'm going to use this rule. So I'm just going to write down that rule. But everywhere there's an x, I'll put a parenthesis. And f of 0 just means plug in a 0 for x. Where there used to be an x, now put a 0. We know that 5 times 0 is 0. 0 plus 3 equals 3. So we can say that f of 0 equals 3. Now we already know that our input value is our x value. X is the input value, and we can also name it the independent variable. X is the independent variable because, I'll make that a little bigger, it's the independent variable because I can choose whatever x I want to plug in to this function rule. So it is independent of anything, it's my choice. But the output value, and we know that the output value is also known as the y value. The y value depends on the x value. Since it depends on the input, we call it a dependent variable. And recall that the x, or the input, is our domain, and the y, or the output, is our range. So again, x is independent, we choose whatever it is, and y is dependent because it depends on what x value I plug in. The output depends on the input. So now let's look at a couple of different function representations. Here's a function. I gave you a name, f of x. And here's a function. It's a different situation, so we're calling f of x something different. So these two have no relationship to each other, two different problems here. And in the middle, I'm giving you a graphical depiction of f of x. Again, a totally separate problem, so they're not all the same f of x. This is like problem number 1, problem number 2, problem number 3. So in problem number 1, we get f of x equals 7 minus 2x. I want to evaluate it for f of 0, f of 1/2, and f of negative 2. Let's start with f of 0. So the first thing I'm going to do is look at my rule. I'm using this f rule for this problem. 7 minus 2 times something. Now instead of x, I'm going to plug in a 0. So I get 7 minus 0, which is just 7. f of 0 equals 7. I've evaluated the first one. We could also evaluate for f of 1/2. f of 1/2 equals 7 minus 2 times something. And now, instead of plugging x in, I'm going to plug in 1/2. Well, I still get 7. And then negative 2 times 1/2 is negative 1. So my final answer here is 6. And I would do the same thing for negative 2. Now, let's say that I wanted to look at this graphical representation. If I wanted to find f of 0, I don't have a function rule that I could plug a value into. But what I can do is go to the x value 0. If I input 0, what's the output? And read up to the output. So when I go to x equals 0, the corresponding output is 4. And I can know that f of 0 is 4. So if I took f of 1/2, I would do the same thing. I would start on my x value, because remember the input, x, corresponds to the x-axis. If I go to x equals 1/2, where's the graph at there? I read out to the output, and it goes to what looks to be 6. Looks like it's this point right here, 6. So f of 1/2 is 6. And I could go to f of negative 2. Now I'm going to go to an input of negative 2. The output is right there. It's at 0. f of negative 2 is 0. Again, I don't have to have the function rule if I have the graph. It's nice to have the function rule though, but I don't have to have it. And we can see that this is actually a function because it passes the vertical line test. I could put a vertical line anywhere along this and only touch one point. I never hit 2 points at the same time. Now you guys take a minute, look at this function, f of x equals x squared minus 4x. Take a second and work out f of 0, f of 1/2, and f of negative 2. So hit pause, see what you guys get, and then I'll work it out for you after you hit play. Alright, let's see what we get when we plug in 0. The first thing I'm going to do is write my function rule, and everywhere there's an x I'm going to put a parentheses. Then I'm going to see what number I'm plugging in. I'm plugging in 0. So I see that f of 0 equals 0 minus 0, which is just 0. Now, we'll do the same thing again with 1/2. I'll write out my function rule, replace all of my x's with parentheses, and then I'll fill those parentheses. Instead of an x, I'm going to plug in 1/2. 1/2 squared is 1 over 4. And negative 4 times 1/2 is negative 2. Now I could make this an improper fraction. I could set it up as 1/4 minus 8 over 4. Now we get negative 7/4. Or I could realize that 1/4 is a nice fraction. It comes out to 0.25. And 0.25 minus 2 is negative 1.75. So f of 1/2 equals negative 1.75. And now when we look at f of negative 2, I'm going to do the same thing. I'll look back to my rule. I'll write out my rule, replacing every x with a parentheses, keeping everything else exactly as it is. And now instead of x, I'm going to plug in negative 2. This is where the parentheses are going to help me out. I see that negative 2 is part of the base. So I get 4, and then negative 4 times negative 2 is a positive 8. My final answer, f of negative 2, is 12. Hopefully you guys got all the same answers. And now let's look at this set. First of all, the question asks, is it a function? Well, I'm given a roster notation full of ordered pairs. So first, let's just plot these points. I've got 0, 1, 2, 3, 4. I've got 1, 5. The next point is 2, 6. The next point is 3, 7. And then the last point is 4, 8. Now, as tempting as it is, we don't want to connect these points. And the reason we don't is because we were only given a roster notation listing specific points by name, not connecting them in between. So there's nothing between these 2 points. It's just this point, 0, 4, this point, 1, 5, this point, 2, 6. So we can ask, is it a function? I can make a mapping diagram and see that there's only one output for every input. But an easier way, since I already have it graphed, is use a vertical line. Let's apply the vertical line test. And as I go from left to right, or right to left, that vertical line never touches 2 points at one time. It's only hitting 1 point at a time. So for every x value that the vertical line lines up with, there's only one output y value. It never touches 2 at once. So to answer the first question, yes, it is a function. Can we write it in function notation? Could I say something like f of x equals? Is there a rule that I could put, like an x plus 1 or a 2x plus 3? And it turns out there's not. I can't write a function notation for this, even though it is a function. It's a special kind of function. It's only these individual points, not the points connecting them. Because it's only individual points, there are no lines or curves connecting anything, we call this a discrete function. And the graph looks like just a bunch of individual points. A discrete function is a bunch of individual points. Again, it doesn't have to be a function. If I put another point that would cause it to fail the vertical line test, it wouldn't be a function. But as long as it passes the vertical line test, a discrete function can still be a function. Alright folks, now if we're told to graph the function f of x equals 3x minus 1, we don't have individual points that we can graph now, so we need to find some so that we can actually put them on the graph. We're going to make our good old friend a table of values. And I'm going to have x inputs, and I will have f of x outputs. Remember, f of x is the same thing as y. So if I plug in, I like to always go a little bit around 0. Start at negative 2, go negative 1, and then 0, and then 1, and then 2. And that typically gives us a good picture of what a graph is going to look like. Not always, but it's a good set of numbers to use. That way we get a couple of negatives, we get to see what happens at 0, we get a couple of positives. Well, let's plug in negative 2 to start with. I'm going to do the same exact thing that I've been doing before. I'm going to rewrite my rule with a parentheses everywhere there's an x. Then I'll plug in the negative 2. 3 times negative 2 is negative 6. Negative 6 minus 1 is negative 7. Now let's do the same thing with negative 1. Write my rule out, plug in my value. That's negative 3 minus 1 is negative 4. And as I'm going along, I'm going to start plotting these points. So the ordered pair, my x and y, or my x and f of x, here is -2, -7. 1, 2, negative, -1, 2, 3, 4, 5, 6, -7. My next point, the x value is -1 and the f of x value, or the y value, is -4. So I'll go -1 down to -4. When I plug in 0, I get 3 minus 1. Plug in a 0. 3 times 0 is 0, minus 1 is -1. 0, -1. 0, -1. And then we'll just figure these last two out and plug them in a second. So I still write my rule down, then I plug in the 1. That's 3 minus 1 is 2. My ordered pair would be 1, 2. And now I'll write down my rule again, plug in my value of 2. 6 minus 1 is 5. So my last ordered pair is an input of 2, an output of 5. Let me graph these last two. We got 1 and 2. We have 2 and 5. Now I've got all my points graphed, but this is not a discrete function. I chose these points just because I thought they would be nice and give me a good picture. But I am not limited. My domain is not restricted just to these x values. My domain is unrestricted, so I can plug any number in, even numbers between -2 and 1. So I need to represent that on my graph by connecting all of these points with a line. Sorry, I slid my screen down there a little bit. I'm going to connect all of these points with a line. And I'll get this cleaned up here just a little bit. There we go, that's pretty good. So all of these points are in fact connected in this function. When I have a function notation, I'm not limited to just the ordered pairs here. These are just ordered pairs that I used to be able to get a feeling for what this graph looked like. And then I need to go back and actually connect them. So again, a discrete function, I'm only given points and no rule. So I can't assume that they are connected. This roster notation only includes these 1, 2, 3, 4, 5 points. So it is a discrete function. When I'm given a function with a function rule, I can choose points to plug in, but I am allowed to plug in any values as long as I'm not restricted. And we'll skip that one. So let's talk for a minute. What is my domain here? Well, when I say a domain, remember I'm talking about the possible x values. What possible x values can I plug in here? I'm allowed to plug in, remember a line goes on forever in both directions. I can plug in values as low as I want to. So my domain is -infinity, that's the lowest, and I can go all the way up as high as I want to positive infinity. There's no value I could plug in here that would give me an answer other than a real number. So I'm unlimited. My domain goes from -infinity all the way up to positive infinity. And what would my range be for this example? How low can it go? Well, it's going to keep going down. As I put more negative x values in, I get more negative y values out. My range goes from -infinity, and it's going to go all the way up to positive infinity. It's never going to stop getting higher. As my x value increases, my y value increases. It'll always increase all the way up to infinity.